So, good morning, everyone. I hope my voice is clearly audible there. Am I audible there properly?
Yes, sir.
Yes, sir.
Okay, good. And the screen, the presentation is also visible there on your screen.
Yes, sir.
Okay, fine. So, today we shall be discussing about a new kind of bonding mechanism, which is ionic bonding. Earlier in the last few lectures, we discussed about the this wonder wall kind of bonding, where dipole-dipole interaction was responsible for formation of the crystals. Now here, and that dipole-dipole bonding was not very strong, and indeed that leads to the crystals with very small cohesive energy. The crystals of noble gas was the example which we discussed. Now today we will be talking about one of the very strong kind of crystals which are formed due to ionic bonding. As the name indicates, ionic bonding actually is formed uh, between the atoms in which the atoms are actually in the ionic form, or the constituent atoms are in ionic form, and the main responsible attractive force is actually the Coulomb interaction or electrostatic Coulomb interaction. So ionic crystals are mainly made up of positive and negative ions, as I already told you. And ionic bonding results from the electrostatic interaction of oppositely charged ions. So whenever a crystal is formed, then some sort of rather we can say due to tendency of atoms to attain that noble gas configurations, many of them, many atoms have a strong tendency to leave their electron, and others have a strong tendency to gain the electron. For example, alkali metals have a good tendency to leave their valence electron, and that is why they have low ionization energies. And on the other hand, you have halide ions, which have a strong tendency to gain the electron, and due to this, they have high electron affinities. So, what will happen is when we try to form crystals of, say, alkyl halides, in that case, those crystals, in those crystals, what will happen? The alkali metals will lose their electron, and that electron, so forming alkali plus means positive ions. For example, in sodium chloride, Na plus ions, and in halide case, these take the additional electron which is left from sodium, and then that additional electron makes chloride ion negative. So Cl negative ion, for example, or halide ion in general negative. And now these electrons are, that electron is no more available with the sodium. It actually is available with the chlorine. So chlorine have one additional electron leading to Cl minus or chloride ion, and similarly sodium has one deficient electron. It has left its electron, so that is existing in Na plus, and that is very stable configuration to them, because now they are in noble gas configuration. And due to this, these crystals, now what is the binding force for such crystals? You have positively charged ions, you have negatively charged ions. So when large number of such positively and negatively charged ions comes together, they form what we call the ionic crystal. Two very important examples which we have studied for ionic crystals is sodium chloride and cesium chloride, right? Okay, Saurabh is trying to connect. Before I proceed further, let me ask you, this is a question from last unit. What is the crystal structure for sodium chloride and cesium chloride? Are the two same, or is there any difference between the crystal structure of the two, sodium chloride and cesium chloride? The formula for both are same, NaCl, CsCl, cesium chloride. So are the two crystal structures same, or is there any difference between the two? Yes, I am expecting your answer. Am I audible there?
Yes, sir.
Am I properly audible? I mean, is there any disturbance or everything fine?
Everything is fine, sir.
Okay, so what is the similarity between, or I mean, what is the, or how does the sodium chloride and cesium chloride crystals compare? That's what I am expecting you to
Sir,
answer.
sodium chloride is FCC
Hmm.
and cesium chloride is BCC.
Cesium chloride is BCC.
So cesium chloride is simple cubic.
Simple cubic. Yes, others? Others? Rahul, what do you think? What is cesium chloride? Is it simple cubic or BCC or FCC? Rahul, BCC. I have given, Sahil says cesium chloride simple cubic, NaCl, FCC. Okay, now this is a very interesting thing. I mean, this is happening because Sandeep and Rahul didn't attend my earlier lectures, maybe because of that, because you joined it late, a little late. But interesting thing you would notice is that cesium chloride indeed is simple cubic. It is not BCC. It very much looks like BCC, but it is not simple cubic. And we have discussed this in very much detail that cesium chloride is indeed a simple cubic. I won't be repeating the things now, but yes, I would recommend you to go to one of our earliest lectures. I have uploaded them on YouTube. Some still there is some task pending on my end because I am not at par with what we do recently. So I mean, I will upload all those lectures, and soon, maybe in coming 2 3 days, we will reach a stage where I will upload today's lecture today itself. Let's hope that will work. Now the thing is that cesium chloride looks like BCC, but it is simple cubic. Now you should try to dig it up why it is so. Okay, that was just a quick revision question. So, I mean, the interesting thing is that both these crystals are ionic crystal. I mean, the bonding mechanism for these crystals is ionic interaction or electrostatic Coulomb interaction. So now we will be understanding these crystals in little more detail. Other very interesting and defining characteristic of these crystals is that the charge density around these atoms is kind of almost spherically symmetric. This is showing, this graph is showing the charge density or electron density distribution in NaCl crystal in one plane, and these are not just theoretical or some intuitive plots. They have been obtained by charge density value here, of course, near to the atomic nucleus, it is high. Because there are core electrons and a lot of them are present near to the nucleus, and then as you go away and away from the nucleus, the electron density keeps on decreasing. But what you will realize is that those electron density contours or constant charge density contours are almost like circles or indeed like spheres. The only deviation happens way away from the nucleus. Similar is the case for chlorine. And what you will notice is that chloride ion are bigger in size. You can notice the radius. the same, I mean, suppose you take 0.1 charge density. So now 0.1 charge density means this is zero point 0.1 for same. These two are same, but you can notice the distance of 0.1 charge density from chlorine nucleus is larger than the distance of the same charge density value from the sodium nucleus. So that is how you can realize that there are two things we can get from here. Size of chloride ion is bigger, and the charge distribution around the atomic nucleus is spherical. Why spherical? Because atoms are almost in now noble gas configuration. They have taken additional electron, and sodium has left its additional electron, finally attaining the noble gas configuration where the electrons are in spherical distribution. Most of the spherical distribution. Let us try to understand kinetics of crystals a little bit. If you see sodium chloride crystal, then let's try to see has been
Hello, sir. You are not audible clearly. Hello.
okay. Yes, yes. Yes, yes. I don't know. Yes, is there improvement? Oh, problem.
आवाज ना आए थे.
Yeah, sorry, there was some network interruption. I hope I am online now. Let me present the screen now. Am I audible?
Yes, sir.
Okay, there was some network problem. Sorry. Okay, so we were discussing this ionization energy thing. So now, I mean, what you can see, this data, this table is given in Kittle's book, where all the ionization, you can find out it anywhere else also, the ionization energies for and electron affinities for various alkali and halide ions. So you can notice that if you take sodium atom in neutral form, that's what they are saying, sodium gas. I mean, atoms are far apart from each other. Then if you apply supply an energy of 5.14 ev, then what will happen? Sodium will lose its electron. You should also pay attention to the size of these spheres here. Smaller. I'm sure you explained why this happens. So means to take off the external electron or valence electron in case of sodium, what will happen? We need to supply this much of energy. That is called ionization energy. And chlorine, when it takes that additional electron, it is smaller in size, but when it takes the additional electron, its atomic size grows a little. And then some energy is released in that process. That is something like 3.61. So if you see the net difference, means there has to be some energy overall has to be supplied for this, isn't it? This is 5.14 energy cost to take the electron from sodium. 3.61 is the energy which is released. So there is some net energy. And this is now finally the experimental data that when two sodium and chlorine atoms come close to each other to form sodium chloride crystal, then the amount of energy which is released, this is an experimental data, comes out to be equal to 7.9 electron volt. Now, if you see these energy differences, then these energy differences are not, it's not that this much of energy is coming from difference of these. So energetics has been worked out in the next slide. Let's go to the next slide for that. Okay, now if we try to do a quick estimation, and then if you, from experiments, we can find out that, okay, the bond distance or sodium chlorine atomic separation actually comes out to be equal to 2.81 into 10 raised to power minus 8 centimeter. It is like 2.81 angstrom. I hope you can convert. Now, if you take one positive charge, means one unit, that is one electronic charge, sodium is 1 plus, right? And one unit negative charge, unit means in the units of electronic charge. Then separate these two by a distance of 2.81 angstrom, and then apply Coulomb's law, and then find out the potential energy of interaction, that is 1 upon 4 pi epsilon naught E square over R, isn't it? That's what is going to be the energy. So that actually turns out to be equal to this one, 5.1 electron volt. So again, I'm not doing it. I'm not working out the details. I leave it as a homework to you. You have to get it done yourself. So that energy comes out to be equal to 5.1 electron volt. Means in case sodium atom and a chlorine atom are placed at this separation to each other, then amount of energy per pair of sodium and chlorine atom comes out to be equal to 5.1 eV. This value, if we compare with the experimental value, that was nothing but 7.9 eV, right? I hope you see this previous slide. That is cohesive energy is 7.9 eV. So this value is comparable. Okay, I mean it is comparable to this previous, the experimental value, but then not exactly the same, right? So now we need to work out, or we need to understand that, okay, where is the difference coming from and how we can explain them, and how in details we can understand the ionic crystal and the bonding aspect of the ionic crystal. The main purpose here is again the cohesive energy. We have to calculate the cohesive energy and explain why do ionic crystal have that specific value of cohesive energy. Okay, let us do small calculation. Am I audible there?
Yes, sir.
Am I audible there?
Yes, sir.
Yes, sir.
Okay, so fine. Now we want to work out that why this energy turns out to be. Now let us do this calculation, a quick calculation. If you pay attention to this previous slide, here, note these values in your copy somewhere. So this is the amount of energy, input energy rather we should say, means the energy we need to invest, right? This is the amount of energy which is released, right? So up to this, we, after, the net amount of energy which is required is the difference of these two energies. And after that much energy is supplied, we will have sodium plus and chlorine minus ions, isn't it? Means a difference of these two energies. So suppose we understand, we assume crystal formation to be happening in steps. So first step is to form sodium positive and chlorine minus ion. Then second step is to bring those ions together at the atomic separation where those atoms are resting, right, to form crystal or equilibrium distance. Now, in first step, the net energy difference would be something like this. This is not first step, this is total energy difference, which should come out to be like this. 5.14 was the amount of energy which was to be supplied to the sodium atom to take off its electron. 3.61 was the energy which was released when chlorine atom gained that electron, that is electron affinity. And 5.1 eV is the energy which is released when sodium and chlorine ions are separated by this much distance, that is the bond length. So what is the net energy difference? This energy difference, because negative energy means energy released. So this is energy released because the positive ion and negative ion are approaching each other. So the work will be done by the system and hence that energy will be released out. Similarly, this is also energy released 3.61 eV because electron is being captured by, chlorine atom. Hence, that is electron affinity, means amount of energy released. Here is energy supplied. So the net difference is negative, means energy released is more, and that comes out to be equal to 3.57 eV. So if the story is okay, I mean, conceptually it seems fine. So net energy which should be released is how much? 3.57 electron volt. Is this story clear till here?
Yes,
is it
sir.
okay?
Yes, sir.
All right. Now, what happens in actual, I hope you have that data of previous slide. So amount of energy overall released is 7.9 eV. Okay. So if we see the energetics, then final cohesive energy turns out to be equal to close to, or that energy difference actually. Okay, this is the energy input which we should supply. This is the energy cost, which is again, this is energy released when chlorine captures one electron. This is the amount of energy when sodium chloride crystal is formed. This is the amount of energy released. So that energy overall comes out to be equal to 6.4 eV. So the main question here is that what causes this difference? Now, if I have put things a little wrong, just a minute, let me cross check. This is the energy, which is total energy, which is released when sodium chloride, this is a cohesive energy, right? So just a minute, let me do a quick calculation. Just now I developed a confusion. 5 point minus 5.14, this 3.61. No, I mean, okay, that comes out to be equal to 6.4 eV. So fine, if there is any doubt on your end, you can ask. I think I have put it right way, not there is nothing wrong. But anyhow, I mean, I will try to rethink over it, but fine. There is a difference of these things. So now the question is how we can actually explain this difference. So I mean, how those ionic crystals actually behave. That is what is the objective of today's lecture. So to explain this, we actually come across a concept of what we call electrostatic Madelung energy or Madelung energy. So basically what happens is that when we have ionic crystals, then we have some positive and negative charges separated from each other, and these are interacting with each other via electrostatic interaction. So you have positive and negative ions arranged over a long distance, because in a crystal what you have, a long range ordering of atomic ions, rather we should say. And then there are two types of interactions possible there. When oppositely charged ions will be attracting each other, and the ions with same charge will repel each other. So in sodium chloride crystal, sodium ions will repel and sodium chloride ions will attract. That's what it means. Okay. Now the ions arrange themselves in whatever crystal structure gives you the strongest attractive interaction compatible with the repulsive interaction at the short range distance. I mean, then what will be the structure preferred by the particular ions? It will be the one which has rather than looking it in terms of the attraction or uh, I mean forces, we can look it in terms of energies. I mean, which structure will be preferred? The one with overall lowest energy, right? So the repulsive interaction between the ions with inert gas configuration are similar to those of inert gas atoms. Of course, repulsive force is there as well. What is the repulsive force coming from? Repulsive force is coming from the electron clouds repelling each other. And when there is one way, I mean, repulsive force is coming from sodium plus to sodium plus and chlorine minus to chlorine minus. That's one kind of repulsive force. But then there is another force as well, which comes from that van der Waal interaction. Sorry, not van der Waal, but this uh, uh, what is that? What was the repulsive force coming from in case of noble gases items? That was coming from Pauli's exclusion principle. Okay, so I mean there is a repulsive force as well. When we try to compress two atoms very close to each other, even in ionic crystal, there will be a additional repulsive component. But that repulsion will be actually among the nearest neighbors only. And there are two types of repulsions now. One is among nearest neighbor, when we try to compress the crystal very much, or nearest neighbors very close to each other, then what will happen? There will be a additional repulsion which is coming from Pauli's exclusion principle. Otherwise, nearest neighbors in ionic crystals will always have attractive interaction, but they can't attract always, right? So they will try to attract, they will attract each other, and atoms will try to come close to each other, but then there will be a lower limit of the atomic separation, beyond which the this one, um, the which force it is? Yes, hello. Am I audible there?
Yes, sir.
Yes, sir.
Okay. Then, I mean, when we close the atoms, when we pack the atoms we try to pack the atoms very close to each other, then that repulsive interaction coming from Pauli's exclusion principle will be dominating, and hence we can't compress them close to each other below certain distance. And one more thing which we need to notice here is that, okay, van der Waal attractive interaction in ionic crystals makes very okay. Then one thing we have seen in is that van der Waal kind of attractive interaction is coming from Yeah, hello. Am I audible?
Yes, sir.
Oh, there was some network problem. I think I was expelled out of meeting. So where did I live? Where I had left the meeting?
Sir, when you are explaining the uh, Pauli exclusion principles.
Oh, okay. So I mean, Pauli's exclusion principle will be leading to the repulsion among the nearest neighbors. They do attract each other because of Coulomb interaction, but at the same time, when we try to compress them below certain distance, the repulsive interaction coming from Pauli's exclusion principle will come into picture, and they can't be compressed beyond that. Okay, so there is a competition between Coulomb type attractive interaction and there is a repulsive interaction coming from Pauli's exclusion principle. So now if we consider a crystal to be made up of many ions arranged together in certain specific structure, then we want now to calculate the energy, potential energy for ionic crystals. And in that case, suppose we pick some reference ion, say ith ion in the crystal, then the total energy of interaction of this ith ion with all its neighbors can be written to be like this summation over uij, where uij gives you the interaction energy between ijth ion pair uh, under the condition that j is not equal to I. I mean, same ion cannot interact with itself. That's the same thing which we did in the previous class for noble gases, right? So now if we want to write down uij, how would uij look like? Uij actually should look like this, where uij means the interaction energy between ith and jth ion is equal to uh, lambda into e raised to the power minus rij over rho plus minus q square over rij, where plus sign. Now you will see, okay, this thing is okay, right? I mean, this is that electrostatic Coulomb interaction, q square over r type. What is this term coming from? First thing is this. So this term is that nearest neighbor repulsion thing. Means earlier we had used that uh, 1 over r raised to the power 12 kind of dependence for uh, repulsive interaction. But then it is found that even e raised to the power minus rij can work well for certain cases. So that is not a universal form. I mean, 1 over r raised to the power 12 is not a universal form. In some cases, this exponential dependence also works fine. And here, this is the repulsive form between nearest neighbor. And this is same standard Coulomb interaction. And interestingly, okay, this will be coming in the next few slides, that, okay, this is the repulsive form that describes the fact that each ion resists overlap with the electron distribution of the neighboring ions. The one which I told you means that kind of Pauli's exclusion principle, or whenever the neighboring ion electron clouds will try to overlap, there will be a very strong repulsion, and that can be represented with this kind of dependence, e raised to the power minus rij type of dependence, where these lambda and rho. So this lambda is actually called the strength of that repulsive interaction, is 1, and is actually if you increase lambda, the rate of decay that is related to lambda. That is why it is related to strength. And the range you can define, okay, when rho is rij, then the uij is equal to something like, if you talk of nearest neighbor, then this will be equal to lambda over e, because when rho is rij, or rij is equal to rho. I mean, rho is a fixed number. When interatomic separation is equal to rho, then this is 1 over e. So that is how we define range. I mean, range of this repulsive interaction is defined as the distance at which the repulsive interaction is 1 upon exponential times the lambda. You can define it that way. So, and these parameters lambda and rho can be determined from lattice constant. So range will follow from lattice constant. Suppose you know the lattice constant, because lattice constant is the value at which attractive and repulsive forces balance each other, and there is no net force on the atoms. And the strength will follow from compressibility. If you try to compress the crystal beyond, then that compressibility will be measure of how strong is the repulsive interaction. So these two things can give you the data of lambda and rho. Anyhow, that's okay. I mean, why we used r raised to the power minus 12, why we didn't use r raised to power minus 12 is because exponential may seem to be the better choice for these kind of ionic crystals. Okay, as I told you that this is not the universal form. Neither this one is the universal form for repulsive interaction, nor this one. In fact, understanding that repulsive interaction, which comes into play because of overlap of electron clouds, is not an easy task. It's a very complex task and involve a lot of quantum mechanics. So that is why we are avoiding to state, or we can't actually state any universal formula for describing that repulsive force. But okay, for this case, we will be using this as a repulsive interaction. I hope everything fine there, and I am audible there. Am I audible?
Yes, sir.
Okay. Is there any question till now? I mean, from what we did till now? Any question from anyone? Any doubt? Any confusion?
No, sir.
Okay. So, that's okay. I mean, we talked about this. So that the total interaction energy is equal to n if there are n formula units. I mean, n units of NaCl. So if there are n units of NaCl, then total energy will be equal to n into Ui, because Ui is the energy of ith ion interacting with all other ions, right? So there will be n such ions. Suppose I take sodium plus ion as a reference ion. Then sodium plus ion, the interaction energy of sodium plus ion with due to its interaction with all other ions in the lattice or in the crystal will be given by Ui. And the total energy of the crystal will be, if the crystal is made up of n formula units of sodium chloride, then total energy will be n times the energy of each sodium ion, because there will be n sodium plus ions in the crystal, right? Then this total energy will be n into Ui. Now, what this Uij, this is what we were actually talking. So Uij indeed is actually equal to this for nearest neighbors, because this kind of repulsion is only among the nearest neighbors, not for next nearest neighbor, because the electron clouds of next nearest neighbors or next to next nearest neighbors won't be overlapping with each other. This situation or this kind of repulsive term will arise only for nearest neighbors. Okay, and nearest neighbors, there are two repulsive forces actually. Sorry, not two repulsive. Nearest neighbors, this is the repulsive force, and because in these ionic crystals or even in sodium chloride, each sodium atom has all chloride ions as its neighbors, nearest neighbors, and each chloride atom has all sodium ions as its neighbors. So the force of the interaction energy or force will be attractive only for nearest neighbors. This Coulomb force or electrostatic force, this contribution is always attractive for nearest neighbors, and otherwise it is going to be plus minus 1 over Pij, the same notation we have used in the earlier case, Pij into R. Now notice one thing, that we are writing the expression in terms of R, the nearest neighbor distance or bond distance. So now we are writing the expression in terms of the bond distance, capital R. So this again Pij-R, again in the same sense as we had done for noble gas crystals, Pij is some number which describes the separation between ijth ions in units of R, the nearest neighbor distance. and this will be plus for same kind of ions for sodium ion interaction. If the ions sitting at this distance Pijr are identical, then this will be plus. If they are opposite in charge, this will be minus. And why? I hope you know, because opposite charges will be attractive and hence give to negative energy, and uh, vice versa, right? Now, therefore, if we follow this notation, then we can write down the expression for total energy, this total energy. This will be N into Ui, as already told here. Then this is N into, let us write it down like this. Now, where this Z is nothing but the nearest neighbors. I mean, how many nearest neighbors are there? And now you will be seeing something new here. Right? This kind of formalism. I mean, there is a term here sitting like this. And then actually there has to be some summation, isn't it? Because Ui contains a summation. So there is no summation here, right? So if you see this term is actually giving, if I pick ith ion, let us take say sodium ion, then each sodium ion will have, say, suppose Z number of nearest neighbors. Suppose in this case, each sodium ion will have Z number of chloride ions. Then those chloride ions are interacting via this repulsive thing. So then what we will be finding, each term, because all chloride ions for a sodium chloride case are at equal distance from sodium. That is why they are nearest neighbors. So that is why this term, there will be Z such terms coming here, and that's what we have written here. Means this summation, when expanded for nearest neighbors, will give you this thing, e raised to the power minus. Now notice here, Rij is capital R. This we have written capital R, because for nearest neighbor, this is nearest neighbor distance. So this will give us the repulsion because of nearest neighbors, plus this term now. Now this term will be, and actually this term is called here, I mean in this whole term, alpha is called the Madelung constant. So how to define Madelung constant? Now you can see here, this one. This is the summation. So alpha is actually given by summation over j prime plus minus 1 over Pij. Now what is Pij for nearest neighbors? It is 1. For nearest neighbors, Pij will be 1. And for nearest neighbors, sorry, what will be this sign? This will be minus. For nearest neighbors, just a minute, let me, okay, cross check this. Yes, so alpha, and for nearest neighbor, okay, plus minus sign is referring to whether we have attractive interaction or repulsive interaction. Okay, one thing which we should notice here is, it's not, I mean, we have taken minus here. So here the things will be opposite. If the charges are opposite, then there will be a plus sign. If the charges are same, then there will be a minus sign. Okay, why? Because we have taken minus already common here. So the things will reverse here. Okay, I hope, I mean, I don't know, is it clear?
सर ये जो UIJ है, इसके अंदर माइनस क्यू स्क्वायर बाई आर की जो टर्म है, वो यहाँ इसमें टोटल एनर्जी में अपीयर नहीं हुई.
कहाँ पे?
मतलब जेड टाइम्स आना चाहिए ना सर,
ये वाला ना?
हाँ जी सर, जेड टाइम्स आना चाहिए इसका भी. अगर वो जेड टाइम हो रहा है तो ये भी जेड टाइम्स आना चाहिए.
बिल्कुल आना चाहिए, बट व्हाट वी आर सेइंग इज, वो इस समेशन में ही बैठा हुआ है. हम जेड टाइम वाले को अलग से नहीं लिख रहे हैं, ठीक है? सो मीन्स ऑफ कोर्स देयर विल, दिस टर्म विल गिव यू जेड, पर वो अल्फा में ही इंक्लूडेड रहेगा. दैट इज अ पार्ट ऑफ अल्फा इटसेल्फ. हम उसको अलग से सेपरेटली नहीं लिखना चाह रहे हैं. दैट इज इनबिल्ट इन द डेफिनेशन ऑफ मेडलन कांस्टेंट. इज इट ओके?
सर ये जो पहले वाले लैम्डा एक्सपोनेंशियल माइनस आर बाई रो है, ये टर्म हमारी रिपल्सन के कारण है.
या
और जो सेकंड टर्म हमारी माइनस क्यू स्क्वायर अपॉन आर, ये जो टर्म है सर, ये कौन से अट्रैक्शन के लिए है?
ये अट्रैक्शन और रिपल्शन दोनों के लिए है। अट्रैक्ट ये जो टर्म है, दिस इज कमिंग फ्रॉम कूलम इलेक्ट्रोस्टैटिक इंटरेक्शन, कूलम टाइप इलेक्ट्रोस्टैटिक, वो आपके नियरेस्ट नेबर में भी होगा। ये जो टर्म है, दिस इज कमिंग फ्रॉम दैट काइंड ऑफ पॉलीज एक्सक्लूजन रिपल्शन, राइट। एंड ये वाली जो टर्म है, वो जो कूलम टाइप इंटरेक्शन होगी उसकी वजह से है। तो वो नियरेस्ट नेबर में भी होगी और नेक्स्ट टू नेक्स्ट नियरेस्ट नेबर्स में भी होगी, नेक्स्ट नियरेस्ट नेबर्स में भी होगी, एंड सो ऑन। तो दिस इज ए लॉन्ग इनफाइनाइट सीरीज, इसमें नियरेस्ट नेबर्स भी इंक्लूडेड हैं। सो मतलब ये जो टर्म आप कह रहे हो, ये टर्म अल्फा में ही बैठी हुई है। मींस अगर ये नियरेस्ट नेबर नहीं होते तो pij शुड हैव बीन ग्रेटर देन 1, राइट। बट हियर वी आर नॉट सेइंग pij इज ग्रेटर देन 1, इट इज 1 एज वेल। सो फॉर नियरेस्ट नेबर्स हम लेंगे pij 1। जब आप pij 1 लेंगे, सो व्हाट यू विल फाइंड आउट हियर, सो pij 1 होगा और ये प्लस होगा, नियरेस्ट नेबर के लिए प्लस आएगा, इजंट इट, क्योंकि माइनस ऑलरेडी कॉमन है। तो प्लस आएगा, तो जितने भी नियरेस्ट नेबर्स होंगे दे विल गिव यू कितनी टर्म्स आएंगी, उतनी ही टर्म्स आएंगी, मींस z टर्म्स आएंगी इसमें से। सो दिस विल बी लाइक ओके माइनस z इंटू क्यू स्क्वेयर ओवर r। फिर इसमें और भी टर्म्स आएंगी, नेक्स्ट नियरेस्ट नेबर्स आएंगे, नेक्स्ट टू नेक्स्ट नियरेस्ट नेबर्स आएंगे। सो ऑल दोस आर सिटिंग इन अल्फा। इज दिस क्लियर?
यस सर।
ओके, तो ये जो मेडलन कांस्टेंट है, दिस प्लेज अ वेरी इंपॉर्टेंट रोल in understanding of ionic crystals. Now distance डिस्टेंस क्या होगी, किस डिस्टेंस के ऊपर इसको रेस्ट करना चाहिए। At equilibrium separation, what's that du over dr should be
Sir, you are not audible clearly.
Okay, Sandeep, let me try if it proves. It's actually the network problem, I think. Yes, Sandeep, is it better somehow?
Yes, sir. Yes.
Okay, fine. So, what we want to discuss is that what will be the equilibrium separation, means the separation at which the potential energy is minimum. And the condition for that is that the derivative of potential energy with respect to the distance or interatomic separation should be 0. And if we take that derivative, now I hope you have that equation in the from the previous slide. You have to take du over dr. So one r term is sitting here, another r term is sitting here. Alpha is some sort of constant, so I mean we will be taking it as a constant. So what will that give us? That will be giving us n into del u over r dui over dr, because we have to take derivative of u total. So this is n into z over rho into lambda. So you know how to take derivative of e raised to the power minus x. So that is what will be coming from this term. Similarly, second term will give us this, and that has to be equal to 0. Is this okay? Are you able to get this expression?
Yes,
from
sir.
Derivative?
Yes, sir.
This is very simple. It will follow straightforward, I think. Now, if we rearrange this equation, I mean, if we rearrange the right-hand side, what we can prove or what we can find out from here is that r naught square e raised to the power minus r naught over rho, this thing r naught square से multiply कर दिया इसको throughout, और रो से भी कर दिया, r naught square into rho से multiply कर देते हैं, तो क्या आता है? So this will be r naught square, rho will cancel here, और यहाँ पे आपका आ जाएगा रो मल्टीप्लाई होके एंड राइट हैंड साइड, मतलब दिस इज जस्ट रीअरेंजमेंट ऑफ थिंग्स। तो यहां से आप आर नॉट को गेस कर सकते हो, ठीक है, कि व्हाट विल बी द इक्विलिब्रियम सेपरेशन। एसआई यूनिट्स अगर आप ले रहे हो देन यू हैव टू रिप्लेस क्यू स्क्वायर बाई 4 पाई एप्सिलॉन नॉट। हम सीजीएस ले रहे थे तो 1/4 पाई एप्सिलॉन नॉट 1 के बराबर, किटल में ये मेंशन किया गया है एक्सक्लूसिवली। सो आर नॉट किसके ऊपर डिपेंड करता है? इक्विलिब्रियम डिस्टेंस। इक्विलिब्रियम सेपरेशन डिपेंड करता है रो क्या था? रेंज ऑफ दैट रिपल्सिव इंटरेक्शन, ऑफ कोर्स उस पे भी फर्क पड़ेगा, उस पे भी डिपेंड करेगा। चार्ज, आयनिक चार्ज क्या है? फॉर एग्जांपल सोडियम क्लोराइड क्रिस्टल में 1 यूनिट होता है, सोडियम पे भी और क्लोरीन पे भी। कैल्शियम क्लोराइड में इट मे बी लाइक Ca 2 यूनिट, chlorine 1 unit. So depending upon what kind of crystal it is, we have to take the value of Q. Nearest neighbors कितने हैं, लैम्डा क्या है, अब इन सभी चीजों पे डिपेंड करता है आपका R naught, the equilibrium separation. So once these parameters are given, you can calculate what should be the equilibrium separation. वो theoretically भी आप निकाल सकते हो. The total lattice energy for crystal of 2n ions will be, so total energy क्या आएगी? We have to actually replace R with R naught. वो आपका जो previous formula था, अगर आप उसको लेते हो, I think मैंने यहाँ नहीं लिखा है, so यहाँ पे आपको R की बजाय R naught की values put करनी है, ठीक है? If you put those values, then you can rearrange. Again, मैं काम करता हूँ, ये आपको एज ए होमवर्क छोड़ देता हूँ, बिकॉज टाइम इज जस्ट अबाउट टू गेट कंप्लीट फॉर दिस क्लास. सो यू टोटल विल एक्चुअली बी इक्वल टू दिस. इसको आपने रीअरेंज करके लाना है कल, एंड यू विल फाइंड दैट यू टोटल को आप इस तरह से लिख सकते हो एट इक्विलिब्रियम सेपरेशन दिस मच, वेयर दिस टर्म, ये जो आपकी टर्म है, दिस इज कॉल्ड मेडलंग एनर्जी. तो मेडलंग एनर्जी हमने शुरू में बात करी थी कि मेडलंग एनर्जी कुछ होती है विच इज गोइंग टू बी इंपॉर्टेंट फॉर आयनिक क्रिस्टल्स. सो दिस एनर्जी इज कॉल्ड द मेडलंग एनर्जी. सो मेडलंग एनर्जी कुछ भी नहीं है बेसिकली, दिस इज क्यू स्क्वायर ओवर आर. पोटेंशियल एनर्जी हुई, कूलम इंटरेक्शन एनर्जी है, एन मीन्स टोटल नंबर ऑफ फार्मूला यूनिट जितने हैं, एक फार्मूला यूनिट की कितनी होगी? क्यू स्क्वायर ओवर आर नॉट. n फार्मूला यूनिट्स की कितनी होगी? n इंटू क्यू स्क्वायर ओवर आर नॉट. बट इट इज नॉट सिंपली n मल्टीप्लाइंग दिस वन, बिकॉज आर नॉट यहाँ पे क्या है? नियरेस्ट नेबर डिस्टेंस है, नेक्स्ट नियरेस्ट नेबर की कम भी तो होगी. सो ऑल दैट थिंग मीन्स लैटिस वाला इंफॉर्मेशन इज सिटिंग इन अल्फा. वो लैटिस वाला इंफॉर्मेशन इज सिटिंग इन अल्फा. सो दैट इज हाउ वी कैन कैलकुलेट द मेडलंग एनर्जी. नाउ वन थिंग इज इंपॉर्टेंट हियर, that for the crystal to be stable, I think that's following up in the next slide. Oh, I didn't put any effects here. Okay, fine, कोई problem नहीं है. So alpha किससे आता है? ये definition था alpha का. अभी alpha को थोड़ा ध्यान से देखेंगे हम, इस तरह की arrangement के लिए calculate करेंगे alpha, किटल में दिया हुआ है ये. And stable crystal structure के लिए alpha must be positive. Why alpha must be positive? You can try to see it from here, because total energy negative होनी चाहिए. अगर total energy positive होता है, so what will be the case? Crystal वैसे ही stable नहीं होगा, मतलब repulsion है बहुत सारी. So for total energy to be negative, यहां से आप देख सकते हो माइनस तो इसी टर्म में बैठा हुआ है, right? Attractive part. So overall alpha अगर negative नहीं होता, positive नहीं होता है, तो total energy ही आपकी positive आ जाएगी, which means unstable crystal. So the first condition for a crystal to be stable is that alpha must be positive, not negative. Okay. Now, okay, alpha की ये definition है. Instead of using this definition, usually we also calculate alpha over r, where r is that nearest neighbor distance. So इसमें कुछ नहीं, अगर आप divided by r करते हो तो यहाँ पे क्या आ जाएगा? rj means distance of ith ion from jth ion. ये टोटल डिस्टेंस आ जाएगी अब. सो अल्फा ओवर आर कैलकुलेट किया है एक्चुअली यहाँ पे इस पर्टिकुलर वन डायमेंशनल अरेंजमेंट ऑफ सोडियम एंड क्लोरीन आयंस या पॉजिटिव एंड नेगेटिव आयंस. सो बेसिकली व्हाट दे हैव डन, यहाँ पे अगर आप इसको रेफरेंस आयन ले लेते हैं नेगेटिव को, ठीक है, इफ यू टेक दिस नेगेटिव आयन एज ए रेफरेंस, सो व्हाट विल अल्फा ओवर आर बी? अल्फा ओवर आर बी क्या होगा? तो नियरेस्ट नेबर्स कितने हैं इसके? दो हैं देखो, और ऑपोजिटली चार्ज्ड हैं। सो ऑपोजिटली चार्ज्ड हैं तो साइन क्या आएगा, प्लस। याद है अल्फा में हमने क्या कहा था, उल्टा हो जाएगा मतलब, है ना। वैसे तो कूलम एनर्जी में तो अपोजिटली चार्ज के लिए माइनस होता है, बट क्योंकि अल्फा में हम माइनस ऑलरेडी यहाँ ले चुके हैं, ये वाला माइनस, सो दैट इज वाई अगर वो अपोजिटली चार्ज है तो प्लस आएगा अल्फा में। ठीक है, सो टू फैक्टर ऑफ टू इज सिटिंग बिकॉज देर आर टू नियरेस्ट नेबर्स, और ये टू फैक्टर ऑफ टू इज कॉमन थ्रू आउट। वाई? बिकॉज नेक्स्ट नियरेस्ट नेबर्स भी टू ही होंगे, next to next nearest neighbors भी 2 ही होंगे, and so on. So that is why this factor of 2 is common throughout. And what will be there, इस sum को अगर हम expand करते हैं, alpha over r calculate कर रहे हैं, so nearest neighbors के लिए क्या आएगा, ये distance r होगा, right? Small rij for nearest neighbor is r, so 1 over r positive होगा. Then अभी next nearest neighbors will be this, and they are same charge, सेम चार्ज है, नेगेटिव नेगेटिव, तो माइनस आएगा, सो माइनस 1 ओवर, और सेपरेशन कितना होगा, 2r, ओके, सो 1 over 2r एंड सो ऑन. सो इस तरह से इसको अगर आप लेते हैं, अल्फा ही निकाल लेते हैं मतलब डायरेक्टली, सो अल्फा विल बी 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 and so on. एंड मे बी आपने ये सीरीज कहीं देखा होगा, log of 1 plus x. इसको अगर आप देखते हैं, then you will be in a position to find out that alpha, because if you put x equal to 1 here, तो ये सारा इस सीरीज के बराबर हो जाएगा. Then alpha will turn out to be equal to 2 into log of 2. This is very standard simple example कि भाई मेडलन कांस्टेंट हम किस तरह से कैलकुलेट करते हैं. For a 3D crystal हमें ये सीरीज अकॉर्डिंगली उस तरह से देखनी पड़ेगी. So to calculate मेडलन कांस्टेंट we usually take help of computer algorithms. कंप्यूटर प्रोग्राम लेते हैं. उसमें क्या करेंगे, we need to calculate where is our nearest neighbors, next nearest neighbors, next to next nearest neighbor and so on. और कितने और what we usually do is, I hope आपने evolved construction पढ़ा था हमने पहले. So आप एक कोई sphere draw करते हो r radius का, और उस रेडियस पे आप देखते हो कितने नियरेस्ट नेबर्स हैं, तो z into वो वैल्यू. ठीक है, सिमिलरली यू गो टू द नेक्स्ट डिस्टेंस, वहां पे देखते हैं कि कितने नेबर्स हैं, उससे मल्टीप्लाई करेंगे, एंड सो ऑन. सो दैट इज हाउ वी कैन कैलकुलेट द मेडलन कांस्टेंट फॉर एनी पर्टिकुलर आयनिक क्रिस्टल. एंड मेडलन कांस्टेंट का फिजिकल मीनिंग मींस इफ इट इज पॉजिटिव देन वी कैन एक्सपेक्ट द क्रिस्टल टू बी स्टेबल. ठीक है, सो हियर आर वैल्यूज ऑफ अल्फा फॉर सर्टेन 3D crystals. ये किटल से ही मैं लिया हूँ. I have not calculated it as such, but okay, these people have obtained maybe. And then you can see that, okay, this is positive for sodium chloride, 1.7. For cesium chloride, it is 1.76. 1.6 for zinc blend structure. So this gives you the Madelung constant for various crystals. An idea, एक idea लग जाता है, ठीक है? So alpha 0 है means crystal is neither stable nor unstable, you can say. अल्फा पॉजिटिव है तो, अल्फा नेगेटिव है तो अनस्टेबल है वो. ठीक है, क्रिस्टल 0 है तो अट्रैक्टिव एंड रिपल्सिव एनर्जीज बैलेंस ईच अदर एंड नेट इफेक्ट इज 0. तो आइडियली 0 मतलब एक बहुत यू कैन से हाइपोथेटिकल सा केस हो सकता है, बट यस अल्फा पॉजिटिव, सो जितना ज्यादा पॉजिटिव होगा उतना ज्यादा स्टेबिलिटी क्रिस्टल की होगी. सो अल्फा का मैग्नीट्यूड कैन बी रिलेटेड टू द स्टेबिलिटी ऑफ द क्रिस्टल, राइट? सो लार्जर इज द वैल्यू ऑफ अल्फा, more stable we can expect the crystal to be, because it is a balance between repulsive and attractive interaction. वहां से ही आता है. This is the table again which summarizes various parameters of ionic crystals. You can just have a look. I mean, here is this repulsive energy parameter, repulsive range parameter, rho, lambda, and lattice energy, experimental and calculate. Now you can see the values of the experimental things, and calculated means ये जो theory हमने अभी discuss किया उसके हिसाब से. And interestingly you will see that the values are in a very good agreement. I mean there's 189.8, 19. So there is a very good agreement between these values. So that's what completes your ionic crystals, how we can understand the ionic bonding among the crystals, and what is the role of this Madelung energy in ionic crystals. So that's all for today. If there is any question, you may ask. And meanwhile, you also please sign your attendance. I think it's too late today. You quickly sign your attendance, then you may leave. You can also type your questions for tomorrow if I have to come with any answers. Yes, Sandeep, you want to say something?
यस सर. सर आपने जो असाइनमेंट दिया है इलास्टिक स्ट्रेन वाला, तो उसके अंदर सर वो जो एनालिसिस ऑफ इलास्टिक स्ट्रेन वही करना है.
एनालिसिस ऑफ इलास्टिक स्ट्रेन्स वो एक स्टूडेंट का क्वेश्चन था कि वो एक्सप्रेशन आ नहीं रहे थे उसके ठीक से किट्टल के.
हाँ
मैं भी
ये
श्रेया.
यहाँ पे इसमें जब हम एक्सपेंड करते हैं इसको टेलर सीरीज एक्सपेंशन लेते हैं
हाँ.
तो मैच नहीं हो रहा सर.
हाँ,
मैच नहीं हो रहा, किटल से मैच नहीं हो रहा.
मैच तो होना चाहिए था. चलो देखते हैं फिर. देन आई विल सी. आप अपलोड कर दीजिए अपने, देन मैं देखता हूँ.
ओके सर.
और कुछ सवाल?
बस सर यही पूछना था.
ठीक है.